So, our project applies the rotational mechanism and thermal physics to solve a real-world problem, which is indoor heat and dryness. By using the NABC framework, we focus on need and approach. Need is the problem and who face the problem, and the approach is our original physics-based solutions. Component of need, people need the fan that's efficient, responsive and comfortable. Our traditional fan, even it spin, but they don't respond to heat change or dry air. So we aim to meet the need for a smart fan that adjusts speed based on the temperature, release mist to relieve dry air and reduce energy use compared to the air conditioner. For our target user is a university student in dormitories, low income family without air conditioner, and small vendor or worker in a hot space.
Next is, how often do people experience this problem and when? The problem is experienced daily, especially during heat peak between 11 a.m. until 4 p.m. The second one is dry season, haze or poor air circulation worsen it. The problem is user cannot adjust fan power manually all day. It will cause discomfort, lead to low focus, stress, and health effect. Next is, how big is the problem? The problem will cause big impact on health, for example like heat stress, dehydration, and fatigue. The second one is sleep and focus, especially for students. The third one is cost, like aircon, which cause high electricity bill. The problem for traditional fan is it has one speed, no mist, no response. Next is, what if the need is not met? Without a smarter solution, first, users stay hot, uncomfortable, and fatigued. The second one, more reliance on aircon. It will cause higher bills and environment harm. The third one is poor indoor air. It will cause dry skin, throat irritation, sinus issues. When the need is not met, people suffer in silence or waste energy.
So, what's our unique solution? We use a thermistor temperature sensor, a sensor that changes resistance based on temperature. It detects rising room temperature and signals the microcontroller. The microcontroller responds by increasing fan speed automatically. We also use a humidity sensor like DHT11. It measures the relative humidity percentage of the surrounding air, and when humidity drops below 40%, it signals the microcontroller. It helps the system detect dry indoor air condition. And lastly, we use the mist spray system. It is activated when humidity level is too low. A small water pump pushes water to a fine mist nozzle, and it releases ultra fine droplets that evaporate quickly in the air. Broad description of the solution. So our solution includes efficient fan blade design. Fan blades are shaped to produce a strong airflow. It also designed to reduce torque and energy consumption. Also, we use microcontroller like Arduino Nano to act as the brain of the system. It receives input from the thermistor and humidity sensor. It controls the fan speed and mist spray activation automatically. And lastly, we use fine mist spray mechanism. It includes a small water pump connected to a fine mist nozzle. It releases a light mist only when the humidity level is low, and the mist evaporates quickly, cooling the air without making the surfaces wet.
Here are the key technical issues that we need to solve. First, sensor calibration. We need accurate sensor to avoid false alarm or slow responses. Second is missed noise surveillance.
The mist nozzle should not disturb the fan's rotation or it could affect airflow. The third is mist control. It is important to control how much mist is released to avoid over-humidifying in the room. And finally, water safety. The system must prevent any water leaks or contact with electrical parts to ensure user safety. And by solving this, we can create a system that's efficient, safe and reliable. So next, let's take a look at technical issue to solve. The first one is the sensor of calibration, which is to avoid false triggers or delayed responses. The next is mist nozzle balance. The nozzle must not disturb fan rotation. And then mist control, which is to prevent over humidifying. And lastly is the water safety. The system must avoid the leaks or electric contacts with the fans.
These eco-cooler Pro have many impact and benefits such as energy efficient, affordable solution, comfort focus and environmental responsible. Energy efficient uses sensor to adjust fan speed and mist only when needed, reducing electricity use compared to air conditioners. Affordable solution designed with low-cost components like thermistor and mini pumps, making it accessible to students and low-income users. Comfort focus automatically respond to temperature and humidity, provide a cooler, more breathable indoor environment. Lastly, environmental responsible optional solar of USB power, reduce environmental impact and promotes sustainable energy use. Conclusion: eco-cooler Pro offer a smart adaptive cooling solution for hot and dry indoor environments and combine rotational mechanics and thermal physics to solve a real-world problem. This eco-cooler Pro automatically adjusts fan speed, activates mist based on environmental conditions. This eco-cooler Pro also designed for students, families and workers who need affordable and efficient cooling. Promotes innovation, energy efficient and comfort using everyday science. A practical example of how physics can improve daily life.